Welcome. Today we are exploring exponential systems where variables are tucked away in exponents. Solving these requires specific strategies to bring those variables down to earth. We will focus on two powerful methods, base conversion and graphical analysis. Why does this matter? Exponential systems model everything from competing biological populations to compound interest in finance. Finding where these equations intersect tells us exactly when two different growth processes reach the same value. The most efficient way to solve these is the base conversion method. It relies on the one-to-one property. If we can write both sides of an equation with the exact same base, we can ignore the bases and simply solve for the exponents. To use this method, you must recognize common powers. For example, seeing the number 8 should immediately trigger the thought 2 cubed. Seeing 9 should trigger 3 squared. This recognition is the key to rewriting your system. When you rewrite a base, you often end up with a power raised to another power. Remember the exponent rule, you must multiply these exponents together. This is a frequent spot for errors, so always distribute carefully. If bases cannot be easily matched, we turn to graphing. By setting each equation equal to y, we can plot them on a coordinate plane. The point where the two lines cross represents the values that satisfy both equations simultaneously. Let's work through an example using base conversion. Here we have a system where both constants, 16 and 8, can be expressed as powers of 2. This is a perfect candidate for our first strategy. Now that the bases are identical, we drop them. We are left with a simple linear system x plus y equals 4, and 2x minus y equals 3. We have successfully converted an exponential problem into a linear one. We solve this system using elimination. Adding the two equations cancels out the y terms, leaving us with 3x equals 7. Dividing by 3 gives us our x coordinate, 7/3. We are halfway to our solution. Substitute x back into the first equation to find y. By converting 4 to 12/3, we find that y equals 5/3. Our final solution is the coordinate pair 7/3 and 5/3. Both equations are now satisfied. In this second example, the bases look different at first glance. However, 9 is a power of 3, and 125 is a power of 5. We will normalize each equation to its own prime base. For the first equation, we distribute the exponent of 2 across the y minus 1, resulting in 2y minus 2. For the second, we recognize 5 cubed. Now we can extract our new linear equations. Our system is now x equals 2y minus 2, and x plus y equals 3. Since the first equation is already solved for x, substitution is the fastest path forward to find our intersection point. By substituting, we find that 3y equals 5, so y is 5/3. Plugging this back in gives us an x value of 4/3. Even with different initial bases, the method of conversion remains consistent and reliable. Sometimes, algebra isn't enough, especially when mixing exponential and polynomial terms. In this case, we graph both functions. We can clearly see two distinct intersection points where the values of x and y are the same for both. To summarize, use base conversion whenever you can express constants as powers of the same number. Use graphing when the equations involve different types of functions that cannot be easily simplified through algebraic rules. Try this quick check, solve 5 to the x equals 25 to the x minus 1. If you recognize 25 as 5 squared, you can see that x must equal 2x minus 2. Solving that gives us x equals 2. Mastering these systems requires practice in recognizing powers and careful distribution of exponents. Always verify your final coordinates by plugging them back into the original equations to ensure they work for both. You've got this. Thank you for joining this lesson on exponential systems. With these tools, you can now tackle complex growth models and equations with confidence. This video was generated by VisionSolve AI.